So hello everyone, I'm Rohit and I'm a PhD student at UT Arlington in Center for Advanced Construction Materials. And from the title of my presentation, one might ask, why do I need to add calcined clay in cement mortar and why do I need to add carbon nanotubes in my cementitious matrix? To answer that, well, the addition of metakaolin, as we all know, enhances the mechanical properties of a cementitious mortar. And if we compare it with traditional supplementary cementitious materials which are available, for example, right here, we have a comparison of the mechanical properties of metakaolin with fly ash. We can see that calcined clay leads to better enhancement of the mechanical properties at 28 days and also at early age. Plus, with calcined clay, we have a higher strength development, and it is mainly because metakaolin is a very high amorphous, meaning high reactive aluminosilicate, and it also has a very high specific surface area, which is more than 10 times of that of fly ash. Another important thing to notice is the availability of clays. They are widely available, whereas other traditional supplementary cementitious materials are not available, mainly because they are secondary products and their availability in future is in question. Not only that, metakaolin also helps us bring down the CO2 footprint of concrete when it's included in the cementitious matrix to replace cement. Here in the table, we can see that the calcination temperature of metakaolin is half of that of cement, which reduces our theoretical heat required for production, which in turn results in 1/3 reduction of CO2 emission during production. But if it is so good, then why do we need to add carbon nanotubes? Well, I showed you that the addition of metakaolin increases these three properties. However, it also leads to a reduction in ductility. But research has shown that the addition of small amounts, 0.1 weight% of cement, of highly dispersed carbon nanotubes leads to excellent improvements in our flexural properties, which can be seen in this load crack mouth opening displacement curve as shown here. The blue curve is for plain mortar. The yellow curve just has 0.1 weight% of highly dispersed CNTs. And this is obtained using 3-point bending test of notch beam specimens. And we can see that the addition of nanotubes, even though in small amount, affects both the post-peak and the pre-first crack in very significant ways. So we developed a research hypothesis that what if we combine them both? So the combination of metakaolin plus CNT might give us a overall enhanced mechanical performance. To investigate it, we came up with a research plan which has a macro to nanoscale approach. First, we calculate the macromechanical properties, modulus of elasticity, compressive strength, and flexural strength for these 4 samples: plain mortar, which serves as control, mortar with metakaolin, mortar with carbon nanotubes, and a mortar with the combination of them both. Then, as we all know that the ITZ, which is a region around the aggregate, is very crucial in determining the macromechanical performance. So it's very important to investigate how the addition of these two materials is affecting the ITZ. So we use atomic force microscopy and semi-EDX analysis to determine the changes happening at the ITZ between the cementitious matrix and sand, because I'm using a mortar sample. However, I'm also adding carbon nanotubes. So there is another interface which is existing at the nanoscale level between the cementitious matrix and carbon nanotubes. And we have used AFM to analyze that, and I'll be showing in the coming slides the results. So for my mixed design, I chose to work with water to binder ratio of 0.4, and the CNT dosage was adopted 0.1 weight% of cement, and they were sonicated using controlled ultrasonication procedure, which is a procedure which we use in our lab group and is patented by Professor Shah and Professor Consta. And the metakaolin replacement percentage chosen in this study is 20 weight%. In literature, the recommended replacement percentage ranges between 10 to 20. For our work, we chose the highest recommended replacement percentage. As mentioned in my first slide, metakaolin is a highly amorphous aluminosilicate. From the chemical composition, we can see that, yes, metakaolin consists mainly of silica and alumina. And from the XRD characterization that we have performed for a commercial metakaolin, we found it to be highly amorphous. We saw only one crystalline peak corresponding to quartz. Here I'm showing you the mechanical test results obtained at 3, 7, and 28 days. The curve on the left shows Young's modulus with time. And if we look at the 28 days value, the addition of metakaolin alone leads to a very high increase in modulus of elasticity, and it's mainly because it is a pozzolan. It reacts with the calcium hydroxide present in the cement to form CHH and calcium aluminate hydrates. So the formation of more hydration products leads to a denser microstructure, which increases the modulus of elasticity. With the addition of highly dispersed nanomaterials, even though it's 0.1 weight%, but it leads to a very drastic improvement in elastic modulus, and it's because the nanomaterials have a modulus in the range of 1 terapascals, and they have extremely high aspect ratio, which makes them ideal reinforcing material. The combination of CNT and metacolin, they give us the best results, and the same behavior is observed for flexural strength. Also, using the load crack mouth opening displacement curve, I calculated these 4 values for flexural properties. Please note that the percentage increase here mentioned in the bracket is CNT plus metacolin with respect to metacolin alone. So we can see that the addition of carbon nanotubes leads to a very high improvements in flexural properties to metacolin cement mortar. And this kind of indicates that the addition of carbon nanotubes helps in increasing the ability of the material to control the coalescence of cracks and subsequent microcracking. Here is the compressive strength results, and we can see that with metacolin, because it's a pozzolan, we have a very high increase in compressive strength, and the combination of metacolin and CNT gives us the highest improvements. One might question that why do we need to add metacolin, because in the above 2 graphs, the yellow and the red points, data points at 28 days are very close, so why not just add carbon nanotubes alone? However, I would like to highlight again that the yellow curve has 20% less OPC. So if I normalize the 28-day values for all the 3 properties shown here for the weight of cement used to cast one specimen of, for the test, then we can see here in this bar graph that indeed there is a big difference, because we are using 20% less cement and we are still getting better mechanical performance. Now, to investigate the ITZ, we have to go down to microscale. We have to use atomic force microscopy, and a sample which is considered adequate enough to be tested with AFM should have a very fine surface roughness. It should not have roughness higher than 100 nanometers, preferably. So we adopted a very extensive polishing procedure listed here. Towards the end, we used iron milling to remove the surface polishing debris. And once we made sure that the surface roughness was well within 100 nanometers, we brought the AFM tip close to the aggregate, as shown in the schematic here. We brought the AFM tip close to the aggregate boundary, well within the ITZ. For our case, because the ITZ is sand and cementitious materials, as based on the literature, the thickness ranges from 8 to 15 micrometer, and the tip radius here for this experiment was 2 micrometer. So we were well within the ITZ, and as shown in the schematic, we brought the tip first in contact with the sample surface, and then we entered a set point force of 100 nanonewtons. So the tip applied 100 nanonewtons force on the sample surface, 100 nanonewtons to stay within the elastic region. And once the sample was deformed and the set point force was reached, the tip was retracted back from the sample surface. As shown in this graph here, the red curve corresponds to the loading. So the tip makes contact with the sample surface, applies a 100 nanonewton load, and then retracts back. While it's retracting back, because it has indented the surface, it experiences an adhesion pull. So that's why we see a lower value here for the blue curve. And we use the initial linear part of this unloading curve to calculate the elastic modulus based on the DMT model. As I told you, F tip is the force applied on the tip. F adhesion is the adhesive force here at the bottom. R is the tip radius, which is calculated during the calibration process. So we have to calibrate the tip before all of this operation is happening. And D is the indentation, which is marked by this arrow. Here are the results for the modulus at the ITZ. With the addition of CNT and metacolin, both, we see improvements in improvements in the modulus of elasticity, and also the higher modulus corresponds to a lower elastic deformation, which is represented by this arrow. Another important thing here to note is that the addition of CNT alone improves the modulus at ITZ, which is very difficult to get using conventional fibers. Also, with this curve, we can notice another thing, that the gap between the blue and the red curve, the gap between the loading and the unloading curve has been reduced, which means that the material is better able to recover the deformation, which hints that the material has now improved resiliency. With the combination of CNT plus metakaolin, we saw the highest elastic modulus at the ITZ, the lowest elastic deformation, and the lowest gap, suggesting enhanced resiliency of the material. The tip radius here used was 2 micrometers, so it gave an idea of average modulus at the ITZ. But we wanted to investigate how the density of the, how the pores of the microstructure is varying and how the modulus of CSH is varying. So we had to use a tip of 8 nanometers, and again we went to a region very close to the aggregate outer surface, well within the ITZ. We chose an area of 10 by 10 micrometers square, and we indented more than 65,000 points, and we got a probability distribution curve which was fitted with a Gaussian curve. So here I'm showing you the results of plain OPC and OPC plus metakaolin. We can see that with the addition of metakaolin, the mean modulus shifts towards right. Now, the modulus range for CSH is between 8 to 32 gigapascals, and from the literature it is mentioned that modulus above 18 gigapascal corresponds to high density CSH, and we see that with the addition of metakaolin, the curve shifts towards right, and we have a higher area of the curve above 18 gigapascal, which gives us a qualitative estimate of the amount of high density CSH we have. Hence, the addition of these two materials, metakaolin and carbon nanotubes, not only improves the modulus, but it also, it improves the modulus, but it improves by increasing the amount of high density CSH. Also, modulus values below 8 gigapascal correspond to pores, and the area of the curve below 8 gigapascal has reduced, meaning we have a more denser microstructure at the ITZ. And these are just the micrographs, and the plots are based on these mapping images, where we can see that the high modulus area, which is the blue and the pink region, has increased. To understand what the modulus improvements means in terms of chemical composition of the CSH, we did we calculated the C by S ratio using SEM-EDEX analysis, and we did perform line scanning from the sand outer surface well into the concrete for a 10 micrometer length, and we did multiple line scans. All of the data points were collected, and then a histogram was developed, which was fitted with a probability distribution curve. And I'm showing you the curve for plain mortar right now. So for plain mortar, we have a mean C by S ratio of 3.75. But for calcium, for CSH, the calcium to silica ratio varies between 0.8 to 2.5. Lower C by S ratio indicates polymerization of the silicate chains. And C by S ratio beyond 2.5 is because of the other hydration products which are present at the ITZ. With the addition of both CNT and metakaolin, and we observe a decrease in the mean C by S ratio with a higher probability of finding CSH. With the combination of carbon nanotubes and metakaolin, we observe the lowest C by S ratio, highest probability of finding CSH, and also the width of the curve is reduced, which means a more uniform microstructure being present. To investigate why we are observing a lower C by S ratio, is it silicate chain polymerization, but is it also happening at the nanoscale interface? We use nano IR AFM, which is equipped, CACM lab is equipped with nano IR AFM, and using this, we were able to go into a region of interest well within the ITZ. We were able to scan an area of 300 nanometer by 300 nanometer using a wave number which is characteristic of the functional groups attached on the carbon nanotubes, and the areas. So basically, we throw a laser of a certain fixed characteristic wave number at the sample surface. If the surface responds to that wave number, it will absorb the laser light, and because of the thermal expansion, the tip is sitting on top of the sample. So the sample expands and the tip deflects, and the deflection in AFM is taken as an electrical measurement, and so we have the values here in millivolts. So the higher deflection or the lighter region here corresponds to carbon nanotubes. So once the carbon nanotubes were located within the cementitious matrix, before I forget, the tip radius used for nano IR is now less than 2 nanometers. So we were able to place the tip exactly at the interface, very close to the CNT and cementitious CNT boundary. So once we are at the edge of the CNT, we can conduct an IR spectrum from 800 to 1800 centimeter inverse. Here I'm showing you just one peak, which is the peak of our interest right now because of the time constraints. And we can see that the peak here at around 1020, which corresponds to the silicon-oxygen bond for the CSH, shifts towards right for the combination of CNT plus metakaolin. Now, a shift towards higher wave number means polymerization. So indeed, there is a polymerization happening at the interface level at nanoscale, which translates to a higher modulus, a higher density ITZ. And now, because we have improved the ITZ at microscale, we see a very high macromechanical property results. And this will also be my conclusion. And I would like to thank my advisors, Professor Shah and Professor Consta, for giving me this opportunity, ACI, Concrete Research Council, for funding our research, Master Builders for providing us with the metakaolin, and to all my colleagues at CACM Lab. And thank you, everyone. I'll be happy to answer any questions.